This lecture is to try to give you an introduction to deep reinforcement learning, and mostly an introduction to reinforcement learning in general. So please interrupt me if there's anything that doesn't make sense, or if if you have any questions. Just say it. I might not see you while I talk, so just tell me if there's an issue. Okay. So with Nicolas, basically what we're going to do is that I'm going to introduce a few algorithms, and then we're going to make a break. Then Nicolas will introduce some practical exercise, and then we'll go back to the class and go through other algorithms, and then we'll make a break again. And the idea is to do several breaks during the class, so you can test some of the algorithms that we introduce, all the way up to the kind of the deep learning algorithms that the state-of-the-art ones. All right.
And maybe for the material, I send everything. So the GitHub link that has been tested in the virtual box. So in the virtual box, you should just install 3 new packages, and then everything should run. So maybe you can start your virtual box and download the material while you are listening to the introduction. Sorry.
Yeah. Great. Okay. Very well. So what's reinforcement learning? So that's a big word, right? We've heard a lot about this. So I mean, if you follow the news, there's a lot of discussions about what reinforcement learning, and the idea of reinforcement learning is learning how to make decisions, right? Learning how to act, how to take optimal decisions by directly interacting with the world or with an environment. A lot of reinforcement learning is done in virtual environments. And the goal is to try to maximize what people call a reward. So what does it mean? So for example, there was this famous paper in Nature by people from DeepMind where they basically used reinforcement learning to teach computers to learn to play Atari games. So the idea is that you try to learn a policy which will map basically the state of the game. In this case, there was basically the pixels that describe the screen to a command, and in this case, the command was basically moving the joystick. So left, right, up, down, and I guess there's 2 actions to fire. So how do you get this policy, and how do you learn that automatically by trial and error? Until the reward to maximize in this case was to get a good score, right? To get the highest score possible in those different games. So this paper kind of restarted the interest of people into using reinforcement learning to try to solve rather complicated tasks, or at least tasks that people thought they couldn't solve 10, 20 years ago, and especially because now we have neural networks in which we can encode rather complicated functions to solve those problems. Another very famous example of reinforcement learning, or use of reinforcement learning, here it's not pure just reinforcement learning. There's a lot of other techniques that are added to that. Is that also from DeepMind, you train a machine to learn how to play Go, and the famous example was that the machine was able to beat the world champion in Go. I think it was in 2016. So in these 2 cases, people were using reinforcement learning to directly discover what is the policy that allows you to win. In the case of Go, the reward obviously is you get +1 if you win, and you get -1 if you lose. So before we go more into detail, so I will focus on the reinforcement learning algorithms, especially for robotics. But there's 2 very good books. I think the one very famous book called Reinforcement Learning: An Introduction by Richard Sutton and Andrew Bartow, that basically explains everything that you need to know about reinforcement learning. So in an hour and a half, I won't be able to give you a comprehensive survey of what reinforcement learning is. I'm just going to give you a few key ideas of how this might work and related to Memo, or to the things we do in Memo. Another book that I find extremely good is not called Reinforcement Learning, it's called Dynamic Programming and Optimal Control, the 2nd volume, which is about approximate dynamic programming. And because it turns out that reinforcement learning is a way to do approximate optimal control. and the volume 2 basically describe many of the algorithms that are actually used in reinforcement learning. So if you read the volume 1 that talks about dynamic programming and tells you everything that you need to know to be able to do DDP, at least the basics for that, the volume 2 basically addresses using function approximator to do that. For robotics particular, there's many survey papers, there's a lot of literature, at least since the late 80s. People have tried to use reinforcement learning in robotics to get robots to do useful things. There's an interesting survey by Jens Kober that was published in the International Journal of Robotics Research that called Reinforcement Learning in Robotics, a survey, and they tried to explain what are the robotic-specific problems that you encounter when you do reinforcement learning. All right, so the typical setup, and I took that from the book of Sutton and Bartow, is this. So you have an agent. In our case, the agent, that's actually a robot, so let's call it a robot. It takes an action, A of t, so the action is basically going to be a control command, right? So you decide to apply torques on your robot. Something happens, so the robot plus in the environment, something is happening. So maybe the robot starts moving, etc. Maybe it starts falling, maybe it starts picking up an object. This changes basically the environment and the robot inside its environment. So an environment is going, in our case, is not a computer game, is not the game of Go, is actually the real world, so physics, right? Or a simulation of physics in many cases. Out of that, you get a new state, right? So you apply an action, a torque, the robot starts moving, so it gives you a new state st+1. That's the new position, for example, and velocity of the robot. Maybe it's new contact configuration, and all the possible sensors you might get, the new values of those. And out of that, you get also a reward that basically tells you measures how well or how bad you're actually doing right now. So the reward, for example, could be measuring how stable you are, or whether or not you're actually grasping an object you're trying to grasp, right? So what we want to, that given set of actions that you can take, and knowing that each time you will take an action, you will change the state of the world and the robot, and you will get a measure of how well you're doing through the reward. We want to maximize the sum of the rewards over time, and the sum of the rewards is going to be a function of the states and of the actions, right? Now we're going to assume that the environment actually is what we call a Markov decision process, which means that the next state, so st+1, is completely defined by the current state that we can measure. So we assume that we can actually measure the state and the actions that we can take, right? And F, so in many of the literature and reinforcement learning, people are going to assume that F is a distribution, so it's not a deterministic function, it's actually a stochastic function, right? So you have a probability of transitioning from st to st+1. So st is going to be a random variable. But for most of the practical purpose in robotics, where basically the world is deterministic, we're going to assume that F is deterministic, and the algorithms are pretty much the same. So all the algorithms I'm going to talk about today, if you want to go to the stochastic case, pretty much you need to add an expectation in front just after any mean or max that I'm going to write up. So it's nothing very particular. But I personally like deterministic system, and I think it makes more sense for robotics. I'm only going to talk about deterministic in this case. And basically the idea is that you want to find a policy pi. So a policy, what is it? It's a function basically that for any state, so if you're in a certain state, S of t, it tells you what to do, right? So the policy is a complete function that maps a state to an action. And the goal is to find basically the policy, and the hope is to find the global policy, so it makes any state for any state, it tells you what to do in order to maximize this reward, in order to achieve a task. All right. So now maybe a little bit of explaining you what's going to be different in typical reinforcement learning problems and the problems we will face in robotics is that the state when you play Go, for example, it's a discrete and it's a countable set, right? You can actually enumerate all possible states. So in this case, for example, the state might be the configuration of all the stones on the board, right? So there's a finite, there's actually a countable number of possible states on the board. In the case of the Atari game, you will have the input of the image of the game. I think for the latest implementation in Go, they also take an image of the game of the board. But basically, you can also, to some extent, enumerate that, even if it becomes more complicated, because you have a discrete number of pixel colors that you can get. But it might be discrete. In many cases, the state is discrete. You can also use continuous state. It doesn't change so much the problem. What is crucial here is that the set of actions in both cases is actually discrete. So to play Go, you don't have many choices. You can put a stone at a number of predefined locations, right? So the number of things you can actually do is you can enumerate and is finite, right? So you can go through all of them. In the case of the Atari game, it's the same thing. The number of actions that you can actually take is actually rather small, right? You can go left, you can go right, you can go up, you can go down, you can press A, you can press B. So there's not much that you can do, and you can actually enumerate those things. Which in robotics, the problem is very different, right? If you look at the state of a robot, well, the state might be the position and velocity of every degree of freedom of the robot, right? And every degree of freedom is not discrete, right? It can take a continuous value from the minimum joint position to the maximum joint position. You might say, okay, but we can discretize that, right? So we don't need to necessarily have a continuous state. We can discretize, which is true. But now in this case, if you discretize the state, what you will have is, for example, if for the first joint you say, okay, I'm going to take 10 different possible values for my joint position. If you have 30 degrees of freedom, so if you have 2 degrees of freedom, then you have 10 by 10, you have 100 possible states, right? Which is a combination of 2 degrees of freedom. If you have 30 degrees of freedom, like a humanoid robot or more, then you have 10 to the 30 possible states, and you can see how it becomes, even if you can pretty much enumerate them, this becomes insane. And the 10 is most likely not enough to describe the different positions that you have in a joint. You might more need like 100, and then suddenly things go, you cannot restore them on the memory. State is still okay. We can work with continuous state, but action space is also continuous, right? What kind of torque we apply on the robot is actually a continuous action. And here this becomes problematic, right? You need to send a torque that is continuous, and that if you discretize, you start to have the same problem that I just described with the state, and you cannot really go through all possible actions to decide, to tell what is, for example, the best action, right? So we will see this in one of the algorithms later, that this becomes an issue to apply typical reinforcement learning algorithms on robotics problems. So as I said, many methods that you can read in reinforcement learning, they are designed for discrete state action models, and this doesn't necessarily transfer to continuous state action models. And here, the idea of the class here is to tell you some of the methods that actually transfer and how you can do that, especially using neural networks. All right. So what's the difference with optimal control, right? These past few days, you've heard a lot about optimal control, about DDP, and maybe you've already seen that we seem to be doing the same thing, right? So in reinforcement learning, we want to maximize the reward, okay, RFT, that is a function of state and actions, okay? And then we have a transition that says the next state is a function of the current state and the action that I take, right? So if I write the optimal control problem, typically we want to minimize the cost, not maximize the reward. We still have a transition model, right? So as we've seen in the DDP tutorial, I think you've seen yesterday, that usually we discretize the dynamics of the robot. So then you basically end up with a model that looks like this. ST plus 1 is a function of S of t and A of t. And that's the typical optimal control in the setup. So you can basically use DDP to solve this problem, right? So why is it different? You would say, okay, there's a max, there's a mean. That's maybe not the same thing, but you can agree with me that maximizing the sum of RRT is the same as minimizing the sum of the minus RRT, right? So minus RRT is going to be my cost. So the main difference actually, and it's actually makes a big difference, is that actually we're going to assume that we do not know the transition model. So we're going to assume that there is a way that there will be a transition, so a function f that will map the current state to the next state, except that we don't know what it is. So we cannot take gradients of it, right? Because we don't have a representation of what it is. So in reinforcement learning, the only difference with optimal control is that we do not know the dynamic model. That's the only difference. And so we're going to be able to use similar techniques, and typically we're going to use Bellman equation, except that we will not be able to take derivatives of f, so we'll have to infer other ways of doing that. But that's pretty much the same thing. Maybe an historical background. So optimal control was originally developed by first by mathematicians, and then control theorists, right? So they were looking at continuous problems, and then with Bellman they started to look at, in operation research, they started to look at discrete problems as well. Reinforcement learning came from computer scientists, so that's why maybe the names are different, and some of the communities at least didn't necessarily overlap for a while. But it turns out they use actually the very same, very similar methodologies to solve these problems, which is nice, right, in the context of memo, because we can have a unified way of thinking about both. All right, so how do we solve reinforcement learning if I don't know the transition, right? So if I knew the transition, I would be able to do optimal control, and I would be done, right? So what people do in what we call model-based reinforcement learning is they do exactly that, right? They say, let's sample the world, so we randomly move, take actions A, and we move from states to states, we collect data, and from this data, we basically try to learn a model, right? To learn the function that transition from S of t, so the function f, to the next state, st plus 1, which is nothing else than digital modification to some extent, right? And once you have a model of the system, then you can do optimal control, right? So I won't talk too much about model-based reinforcement learning, but the gist is that you basically sample the world, try to get a model of the world. Once you have that, of the robot and the world, once you have that, you can just do optimal control and you're done. So there's not much to be said there, and then you can basically take your favorite regression method or your favorite system identification method to basically learn this model. This was used actually very successfully. So since a while, actually, it's been a long time that people do model-based reinforcement learning. In robotics, I don't know if it's the first example, but it's one of the, I think, very first examples of that. Chris Atkinson, Stefan Schall, they basically do exactly that. They fit linear models, and then they do LQR. They learn linear models of certain dynamics. They do that for juggling, and then they fit an LQR, and that's the optimal policy, and they're done, right? So optimal control. This was kind of put back into being a fancy approach recently by Sergey Levin and Vladimir Koltun with the guided policy search algorithm, which pretty much is the same idea, right? Except that at the end, once they get a bunch of LQRs, instead of doing LQR, they do ILQR, because now we can ILQR. They still get a policy, and then at the end, what they try to do is that they try to fit a neural network to generalize the policy from different trajectories. But the gist is exactly the same idea, right? You fit linear models, and then you do optimal control on that. Interestingly, the ICML 2013 paper seems to completely ignore what was done in the past, where pretty much already implemented those ideas. Anyway, all right. So that's for model-based reinforcement learning. So we're not going to talk too much about that. We're going to talk about model-free reinforcement learning. So what is model-free reinforcement learning? Well, the idea here is that instead of trying to learn a model and learning the transition, we're going to try to learn directly the policy. So we're going to ignore the model, and we're going to ask the questions, can we directly, from trying separate actions in the world and seeing how the state goes from st to st plus 1 and what kind of cost we incur, what kind of policy should we choose, and or typically, can we approximate a value function that allows us then to get the policy. And all the algorithms that basically are related to these things are called pre-learning, actor-critic algorithms, and policy gradient algorithms. And that's the algorithms I'm going to describe today. All right. So before going into these algorithms, I would like to refresh. We need to go back to Bellman, and we need to basically remind ourselves about the Bellman equation, because pretty much everything is based on that after that. So I rewrite, I cheated a little bit. So now I write the minimization problem over the actions, the possible actions, the minimization of the cost over an infinite number of steps. So I have an infinite horizon now, and I'm going to assume that now I need to add a discount factor, gamma. So gamma is going to not be a small number, close to 1, but smaller than 1. So typically a 0.999 or something like that. That just makes sure that as I sum over infinity, the sum is finite, right? So basically gamma to the power of t goes to 0, and everything works out. So that's just a discounted cost. And otherwise, I assume that I know the transition model. S t plus 1 is a function of s of t and a of t, and that's it. So if you go to Bellman equation and you do that in the infinite horizon case, basically you can write the dynamic programming equation. So the value function s of t. So the value function is, just to remind you, is the optimal value that we can obtain if you would use the optimal policy. So assume that you have the optimal policy. If you apply, so you apply the optimal policy and you instate s of t, v of s of t tells you what will be the minimum of the infinite sum that I've written above, right? So the value function just tells you what would be the best, the minimum value that you can get, assuming that you apply the optimal policy. What is nice when you apply the dynamic programming equations and you basically when the sum goes to infinity, it turns out that you can write it this way in the discounted case. So we said that the value function at s of t is equal to the minimum over all the actions a of t of the instantaneous cost. So c of t is a function of the cost c of t plus gamma times the value function at the next step, the next state, right? So remember, s t plus 1 is a function of s of t or a of t, so when you minimize, you need to minimize also over v of s t plus 1, because it's a function of the action or the control you're going to take. All right, so this Bellman equation is interesting because it's a stationary equation. It means that once you found a function v, basically this function v needs to satisfy this equation, and it's stationary, means it doesn't move anymore once you found it, right? So an interesting theorem says that v actually, so if you can't find a function v, it actually there's only one solution to this equation in the class of bounded function, and the value function is actually the solution to this equation. So basically this equation, solving this equation gives you necessary and sufficient conditions for optimality, right? So if you can solve this equation, you're done. You found the optimal value, so you basically solve the minimization problem, and once you found the optimal value function, then you can read out what was the a of t from the minimization, and this gives you the optimal policy, pretty much in a nutshell. All right, so how do we solve this equation, right? So the first algorithm, called value iteration, is just going to use a very interesting property of this function to try to iteratively get a better guess of what is v, until we converge to what is the actual true v. So here we assume that we have a discrete number of actions and of states such that we can enumerate them and we can store them in a table, right? So we can go through all possible combination of s and a's. So value iteration, how does it work? We start with initial guess for v. So we don't know what v is, but we're going to start with initial guess v0. Okay, it could be anything. So we start with this initial guess. Then what we do is that we, for every state, we're going to evaluate, iterate the Bellman equation, assuming that v0 is correct. So we said that how do you say that? So the next v for every state, so v1 is going to be the minimization, assuming that the vn on the right side is actually the v0 for the first state, right? So you compute the next v so you have a table, right? Of possible. So on one side you have the s, on the other dimensions you have the actions. You compute for every possible state the minimization over all possible. You have I'm already going one step too fast. The value function is just indexed by all the possible states, so there's no action, right? So it's a one-dimensional vector. So you start with your V0, that is for every possible state, right, is going to have a certain value. And V1, so the next V, for every single state you evaluate what is the minimum over the actions, right, of this function. And then you get the next V, and you keep doing that until you converge. And what is interesting is that V of n, when n goes to infinity, converges to V. So at some point, V is going to be the actual value function that you had, that you were trying to find, and then you solve the problem, and then you have the optimal value function, and from the minimization, you can read out the optimal policy, and you're done. This is assuming that you can count the states and minimize over the actions. Okay, how does it work? So here, the typical canonical example, we're going to say we want to get out of the maze, so you start at you have a maze, so here you have the gray box, that's an obstacle you're not allowed to go to. You want to reach the green, so the green values -1. If you reach the bad, if you reach the red, this is bad, so you get +1, right? That's your cost. You want to minimize the cost. And the possible actions is you can move north, you can move east, you can move west, you can move south. And we're going to use discount factor of 0.9. So what we do is that we initialize V0 by arbitrary values, right? So we're going to set 0. Then, for every single state, for this V0, we're going to compute what is the mean, that is the current cost. So the current cost, if you're in a cell that is not neither green nor red, the current cost is 0 in this case, so it's going to be trivial. And then we take the mean, that we take the action that allows us to get the mean next value function, right? So for the first update of the Bellman, since if you're not close to the green one, you cannot move to the green. Nothing basically gets propagated to the other cells. There's only the first cell that gets a new value function. If you're close to the red one, you basically don't move to the red one. You move to something that costed 0 before, so nothing happens, and then you get the new update of your value function. So you do that for every single state, right? You do a second iteration, so you redo that for all single states. So you can see now that the value function an estimate starts to propagate among other states. And then you do a third iteration, and it propagates again, and then you do a fourth one. And then after 10, you start to have other values, but you see that as the table starts to change, so these are all the value functions for all the possible states, right? So we keep doing that until we converge, right? So after 100 iterations, we have these values, and after 1,000, this doesn't change, so we're good. We found basically a stationary value function. So now we have converged, we found the optimal, so the value function, and the policy you just read out by following the action that create the lowest next value plus current cost, right? The current cost is 0, and the next value is basically you look at where you need to move such that you can get a lower cost. So for example, if you're on the bottom right case, you have -6.5, and where do you need to move? You move to the case that on the left because you get -7, so that's better than if you would move up, you get +10, right? And then once you're in -7.29, where do you move? Well, you move up because this is gives you -8, and this is better than the -6.5 on the left or the -6.5 on the right, right? And so you decide where you move from every point, and then you get this pattern, and that's the optimal policy. So when you start from any state, you just apply move up, move right, or move left, and then you will guarantee to reach the goal. Okay, so that's value iteration. This works also if the system is not deterministic. So here you take, instead of taking the next best thing, you take the expectation over all the possible actions you may take. But otherwise the same idea. All right. So value iteration is great. It allows us to solve a complete globally optimal control problems. Now you might see a few problems, right? If you have a lot of states and a lot of actions on which you need to minimize, this is going to be very practical, and it might not converge really fast. So there's another algorithm called police iteration. And a police iteration, well, you start with, instead of reading out the policy at the end, what we do is that we start with initial guess for the policy, right? That we randomly start. We also start with the initial guess for the value function, so as before. And then what we do is that first we evaluate the policy. So the idea is that we iterate the Bellman equation, but we don't iterate the Bellman equation assuming that we basically use the current policy to decide what is the transition. So we don't do a minimization over all possible actions anymore. We just apply the policy that we are guessing, and we compute for every state, what would be the next Vn plus 1. And we do that until Vn actually is going to converge. It's not going to be the value function of the optimal policy. It's going to tell you what is the cost that you will get, assuming that you only use the current guess of the policy. From that, you do a policy update, where basically, given the current guess for the V, you compute the policy such that you take the argmin of the transition, so the instantaneous cost plus gamma times the value function. So this will give you a new policy. And then you go back to the policy evaluation step, you reevaluate your policy, you get a new V, you do an update of the policy given this V, and you keep doing that until the policy doesn't change anymore. And this is called policy iteration, so it's kind of a variation of value iteration, where you do a value iteration in an inner loop inside the policy evaluation, and then you update your policy as you go. Right? And this is kind of going to be reminiscent of what we're going to see when you do actor critic algorithms in reinforcement learning. All right, so now I've been talking for a long time, and now you're going to ask me, say, okay, but I was supposed to talk about learning, right? So everything that I've discussed now so far has been deterministic, has been assuming that I know exactly the transition model and I can compute those things. So how do we do reinforcement learning? Well, the idea is actually we're going to do exactly the same thing. So we're going to do value iteration. So Q-learning is actually, I call it value iteration with a twist. Is actually we're going to do value iteration, but we're not going to work on the value function. We're going to work on a slightly different function. So we're going to introduce what we call the Q function. So instead, do you remember the value function is it's a function of the state. Say if you start at state S, what is the cost that you will incur if you apply the optimal policy, right? So now what we're going to say is that the Q function is going to be indexed by the states and the actions. So now instead of having the one-dimensional vector that goes through all possible states, we have a two-dimensional system, assuming that you can discretize the states and the actions. You have a two-dimensional system where you go through all possible states and all possible actions. And so this function will store for each a pair of state and action the cost that you will incur if you choose action A of t at time t, and then you just apply the optimal policy afterwards, right? So you just see, let's assume I just choose A now, so it might not be optimal, it's just a random action I choose A. What cost do I get if I would do that, transition, and then I just apply the optimal policy? So formally this looks like that, right? You say Q of S of t and A of t is just the current cost that I will get if I use action A, and then plus gamma times the value function, right? And the value function being the cost you get if you do everything optimally afterwards. So basically what it tells us is that that's equivalent to saying that now you can see that the value function is going to be the Q function for which you minimize over A of t, right? So given a function of state S, you take the Q function for this state S, you find the action that actually minimize that, and this is actually equal to the value function. All right. What is nice is that now I can plug in the Q function inside the Bellman equations, right? By using exactly the equations that I just showed. So it also satisfies Bellman equation. So here now we don't have the value function anymore. We have the Q function. So Q of ST AT is going to be the instantaneous cost. So what is the cost I incur now, plus the gamma times the value function, which is the mean over the next actions of the Q function. Okay, so we have the same, almost the same equation that we had before for the value iteration steps, except that now what we have is that we can go through all we have a function that can go through all possible actions, and the only thing that we need to look at is assuming that we incur an instantaneous cost C of t if I can measure C of t, the hope is that then I can get an evaluation of what Q of S of t and A of t is for every possible S and every possible A's. And by doing that, basically, I'm going to try to get an estimate of all the cost, the cost I will get taking every possible action I might get, right? And from that, I will try to infer what will be the value function. So why is it useful? It's useful here because now if I randomly take an action A and I don't know what is the state transition model, I will move to a next state S, and I cannot compute basically what the next state S is, but I can store it. And then by using a pair of what is S of t, what is the action that I choose A of t, that can be anything, I don't know what it is. And then what do I get as a cost? This I can measure. And what is the next state I go to, which is S of t plus 1, this I can measure as well. I will get all these numbers, and I can try to solve these equations given these samples that I get from the real world. All right, so let's assume you choose a random action A and observe a reward C. What did we get? Assuming that your Q function was correct. So then you should have, if things were correct, you should have this, right? So you should satisfy those equations. Now, our guess of Q, we don't know what it is, right? What we want to find is that we want to actually learn what Q is, but we don't know what it is because we don't know what is the optimal value function. So if it was correct, we would have this equation. If it's not correct, basically we can infer the error, right? So if it's not the case, we can estimate how wrong we are. So let's assume that the right side is correct. That's our current guess. Then you can evaluate what the left side would be. You can compute an error, and then you can update the left side by saying I want to minimize this error, right? I want to minimize the difference between what I get on the left and what I get on the right. And you see that you can actually compute what I get on, assuming you have a guess of what is Q, and you have tried something in the real world, so you get a transition, you get from S of t, you did some A of t, you got a cost, you got the next state. You can actually evaluate the left side and the right side of this equation, right? And if you have a discretized actions that you can go through that, you can actually minimize by just, so the mean on the right side, you can go through all possible actions and they just take the smaller value, right? So you can get this error, and the idea of Q-learning is exactly to do that, say the new Q that I'm going to update the next time I actually generate a transition from S of t to S of t plus 1 taking an arbitrary action A. I'm going to do 1 minus alpha Q, so basically I'm going to keep my current estimate of Q, but I'm going to multiply by 1 minus alpha, so I'm going to decrease it a little bit. Alpha being a number that is called the learning rate, so it's going to be a number between 0 and 1, and typically it's going to be closer to 0 than to 1. And then I'm going to compute the actual error that we make, which is basically C of t plus gamma minus of Q, assuming that we use the current Q, right? So this I can estimate, I can evaluate as well. And then I update the Q new. So the Q new tries to basically minimize the difference I see between the left side of the equation, which is Q, and the right side of the equation, which is C of t plus gamma mean of Q. Yeah? And this we can do that by just recording what happens when we take the random actions. Alright, so this algorithm was introduced in 1989 by Watkins, so it's actually rather old. As I said, alpha is the learning rate, and so the algorithm looks like that, right? So if you have a discrete state action space, and a moderate size for this space, so you can enumerate basically the states in the action, and you can store the Q function as a table, right? So a two-dimensional table, where in one dimension you have all the states, on the other dimension you have all the possible actions. So Q-learning using this table works this way. You choose a small alpha, which is the learning rate, so typically you choose it very small. You choose a small epsilon, which is going to be a way to kind of randomly generate actions. Then you initialize your table, right? Two-dimensional table. Remember before in value iteration we had the one-dimensional table, now we have a two-dimensional table. You generate it arbitrarily, whatever it is. Then for each episode, so you're going to generate what we call an episode. Is going to be a sequence of actions that go from you start with the initial state, you try something for a certain number of steps, you see what happens, and then you record everything. So that's an episode. Then you stop, you're going to do an update, and you do it again. So you start from initial state, so you initialize your system however you want. So for example, you start at 0, or whatever might be the initial state. Then for every step t in the episode, so maybe it's a duration for maybe a few seconds, you perform some actions. What you do, you choose what to do, the action, given the current state, by using a policy from Q. So for example, we are going to do what we call an epsilon greedy policy. So the epsilon greedy policy is going to say that if the epsilon is small, right, a small number, with probability 1 minus epsilon, I'm going to take the mean, the action that minimizes the Q function at state S of t. So that's basically my current guess of what is an optimal policy. And with a probability epsilon, I'm going to do something else that is completely random, right? So I choose the random actions among the set of actions I have. So the epsilon greedy policy allows me to randomly select actions that I've never evaluated, such that I can explore a little bit what might happen if I do something I don't know, I've never tried before. So I take this action, so I actually implement this on my robot and see what happens. I observe a cost, so I see what is the I evaluate the cost, right? I get a number, and I get the next state, right? And I do that for maybe a few seconds, so I get a series of states, actions, and transitions to ST+1, and the cost, right? And then at every step, I'm going to update the table. So I'm going to update for the state that I just was in, so S of t, and for the action that just took, so A of t, so this one cell in the table, I'm going to update it using this rule, right? So I measure what was my current guess of Q of S of t at. I measure what is the cut that I got, and I take the mean over Q of ST+1A by enumerating through all the possible A's, right? And I do that until I converges. And ideally, if I do that until I converges, I will get converged to a Q function that works. And then when I have the Q function, if I take the mean over A of this Q function, I have the optimal policy that I should apply. And that's my reinforcement learning algorithm. All right, so I've been talking a lot. Now, I guess it's time to make a break and to actually see how it works. So Nicolas now is going to take you through exercise. We're going to do Q-learning with the table, right? So we're going to store the Q function into a two-dimensional table. And on the problem, we're going to discretize states and actions. And maybe, Nicolas, you want to take over?
Okay. So me again. Sorry. For the last set of exercise. So this time I had enough time to validate the code. It is working in the VirtualBox. Sorry again for this mistake on the DDP class. So at least for the VirtualBox it's working. I guess for other Ubuntu 16 or 18 it should work as well. So you just need to install the TensorFlow framework using pip. It's working very well. And apparently it's also needing TK something. So TFlearn is a set of shortcuts on top of TensorFlow to make the syntax a little bit easier that I'm using. And TK inter is something for Matplotlib. I was surprised that I needed that. And then you have a bunch. So this time I did not make Jupyter, so it's not really exercise. It's really some toolbox to play with. So you have a set of scripts. The first one to use is Qtable. It's a very simple one. I don't know, Ludo, should I? Well, we did not ask for questions, right? So while you are setting up, if there is any questions, I think Ludo should be able to hear you. Maybe you want to stand up and go in front of the camera for that. Oh, you don't want?
I hear.
While Ludo was talking, I did a little bit of documentation of the code. So if you want to pull, you will have more explanation in the text. Ludo is still here, but I put the first example here. So here we optimize for a very simple system. So the system that I have chosen to use is an inverted pendulum. The display is done in JPEG viewer, so don't forget to run the JPEG GUI before you start the Python script. As soon as you run the Python script, you will see some verbose display explaining you what the algorithm is currently doing. So if it's blocked, it's because you forget to run the JPEG display. And so this inverted pendulum, is a continuous system. You have continuous input for sure. The state is continuous. That's the angle and the velocity of the pendulum. The control is also continuous. That's the torque you are sending to the pendulum joint. This torque is very limited, so that you cannot raise the pendulum from anywhere. You have to swing to increase energy until you are finally standing up.
Which file is it?
That's the Qtable. Qtable file.
How do you start the rendering?
JPEG GUI.
But from the same directory or not?
No, whatever.
It's not.
It is. Come on, I try. In fact, I alternate a little bit between the unicycle and the pendulum. The pendulum is a very basic example that is very easy to discretize, and it's very easy to get good results even if you have a rough discretization. So it's good for the simple example. And then I had in mind that I put this pendulum for the Qtable. No, I put the unicycle. So it's a bad choice because it's taking more time. The pendulum, the unicycle, if you want to park it with a decent precision, decent accuracy, then you need to discretize something like 1,000 control, a little bit more for, so 10,000 I think for the state. So you start to have something big. So what he's doing here in the output is displaying the number of episodes. So an episode is a trial that the system is doing. You are trying to run the car during 50 iterations, and after the 50 iteration, you look how close you are to the solution. The solution is to get there at the 0, 0. So you want to be at the origin. So you can see that as a maze. You have many states. You have many walls because you cannot drive from one state to the nearby state directly. So it's a state in dimension, I think 4. You have x, y, cos theta, and sin theta. And the system has to go. There is only one exit from this maze. That's the very center of the world. Okay? And it clearly does not know which state is the center of the world and where it is, how it is connected. So it will explore the environment. And at each episode, you get either 0, you did not get out of the maze, or 1, you managed to get out of the maze.
The validation is too fast on my machine. I can't see okay.
So in the very beginning, well, you have a display every 20 episodes. And so you get a score over 20 every 20 episodes. So in the beginning, you get 0. So he's never able to get out of the maze, which is normal. I have 10,000 states to explore, and I only have 50 iterations that can get me in this out of the state, out of the maze. So it's very unlikely that going randomly inside the maze, I can go out. Then he starts to collect some rewards. So some random executions, they are close enough from the exit of the maze, and just randomly in 50 iterations, he can get out. So now you don't need to go out exactly in the middle of the maze. You just can reach one state where you know how to go out of the maze. So instead of having only one point that you should reach, you have a small region. So it's more likely that you get some success. So after some iterations, he start to, so here you see, same on your computer, you see that instead of having only zeros, I start to have a lot of 1, 2, 3, even sometimes he's able to get 4. Here we have a 4 over 20. So it's still very bad, but it means that the region of exit, the region that if he reaches this region he can succeed, start to grow. And while it grows, we have more and more data, so trajectories that are successful. So more and more this region where you know how to do grows again. That's something maybe we should display it. So any states where when you reach this state, you can go out. It could be easy to print, and we will grow. We will see a ball growing like that. That's the number of states that is likely to succeed. Once the region is big enough, well, any point you take, you go randomly, you will reach this region, and soon you will start to always succeed. So here we are in this case. We go to 20. Not yet, but we have 18th, 17th very often, and once it's enough, everything will be 20th. So now if I stop the training, I can see how it's working with the render trial. So render trial will be I take one random state and I roll out the policy. So this is how we manage to go. So if it's too fast, just put a timer in the render trial loop.
Yeah.
That's why the code is provided to play with it. Are you playing with the code at the same time, Ludo?
No.
It's very funny.
No, I played with the code already. I
You already did
that.
that.
Actually, that's how I learned how Q-learning was working.
Render trial. I don't have this.
So when you do render trial, it starts from a random state.
Yes. And then you roll out the policy for 60 iterations.
I think it rolls out until you get a reward. There's a maximum number of iterations of 100.
And that's
If you
it.
get a reward,
Oh, it breaks. Yeah, you're right. So we stop when you get the reward. So in this example, the system gets 1 as a reward.
I cannot see the schedule.
Oh, so here, for example, apparently it does not know how to. That's a failure. From this state, it does not know what to do. So basically, this state was never met during the training phase. And here we have a table. So every column of the table corresponds to the Q value of the corresponding state. There is absolutely no regularization or any approximation that can make the column be something if you've never allocated a value in there. So from this state, it never been in this state, so it does not know how to go out of this state. There is no way. This column is full of 0. It's just doing nothing. Okay, well, that's a very simple algorithm. So that's why it's slow to converge. The representation of the policy is huge. That's all the possible value of the policy and the value function. So everything, and there is absolutely no generalization capability. Also, with a control perspective, what we did here is minimum time, or something similar to minimum time. So we get 1 if we go out, and 0 otherwise. And the behavior of the system is quite bad. No, it is not. Sorry, it's not minimum time. It's feasibility. So you are just trying to solve the system. Whatever trajectory is going out of the system is acceptable. Then there is nothing that is tending to smooth the trajectories and get a better result. Okay.
So you simply need to modify the reward to -1 every time you're not.
Yes. So yeah, that's one of the aspects of. Modifying the reward is very easy, and we can get it's the same optimal control. So having a reward or a cost function makes very easy to tune the system, except that the algorithm is very sensitive to the way that you tune the cost function and the reward function. If you change the reward, it's very possible that the system is not working anymore. But yeah, that's the point. Okay, so that's just an appetizer. It was just to check basically that the system is working. There is nothing much that you can do with that. It's slow to converge, so you can't really try to play several times. We'll see now a more complex algorithm that we can play with.
Do we control humanoids with that?
With a Q table? So say you put what? You want to discretize the state with 10 iterations for each joint? Do the math.
Oh, and so you have to find the reward by randomly sampling.
So that's what we are doing by optimal control. So with optimal control, we have a cost function or reward function, and we hope to find a trajectory. So it's not impossible. Maybe it's too difficult to find the full policy or to represent the full policy, but finding one solution is something that we believe is feasible. And in any case, planning is doing that. Okay, so we have the capability to compute one solution. The stake of learning is not to compute one solution, it's to compute all the solutions. But there is no impossibility in that.
Yeah, but I mean, if you have a sparse reward, you have a very small probability of finding it by doing a random walk with probability epsilon.
Yes. And that's the same in that.
So,
Carlos has a question.
Is there
Carlos
an
always
advantage of these simple this problem? So I have to restart. No problem.
For the Q table? No. It's just pedagogy. Maybe ask Ludo if somebody is using that anymore, but no. That's a very old algorithm, it's working very bad. Just for pedagogy. It's very easy to understand, very easy to employ. Not use the
Anyway, I'll handle.
No, it's AGV. So,
it's based on HTTP, that doesn't mean that you can prove that it converges to something.
yeah, it's proved to converge. It's the same algorithm, it's working well, but the representation is huge. You need to explore the entire space. No way that you can avoid going to one region of the space. But then if you do that, it's converging to the optimal.
So now it's not converging because you're not exploring the entire space.
Yeah. So for all the trials that I have done, it's converging to something. Just for the state that we did not explore, there is no value.
Yeah, it converts to something, but it's clearly not optimal policy.
Well, the reward that I put is very bad. So it's only 1 and 0. Well, there is a discount that is smoothing just a little bit, but very, very little.
But that's what you're supposed to do, right?
Yeah, but in practice, no.
It doesn't work, but that's what you're supposed to do.
No, they pretend they will never tweak the cost function, but at the end, they do tweak the cost function.
So the best reward for this case would be -1 for all the reward. Then you will incentivize for the controller to get out as soon as possible, so it becomes a minimal time problem. Right now, it's actually really bad because you shouldn't have discounted. If you discount it, then discount actually incentivizes to get out early. Because you get out early, you get the 1 earlier. Whereas you get out late, you discount as if you didn't get out.
Yeah.
But also, in regard to your question in table, the table is actually one of the cases you can prove convergence. Once you scale up to a neural network, there is no convergence result.
The 0-1 reward is on the pendulum. I get confused. On the Cosmo, I have a minimum length trajectory plus the terminal cost of +1 if you reach the solution. Okay, so I think it's enough for this simple example, and I think I can go back to Ludo if there is any question anymore. Same, since Ludo will take the floor now. If you are not able to run the exercise, just call me. I will help you while Ludo is continuing.
All right. Should I share my screen again? Do you see me again? Yeah.
Yes.
All right. Do you see my screen?
It's small yet, but he wants me to share my screen as well. No, that's fine. Okay, very good.
So you good? You hear me? You see my screen again?
Yes.
Everything fine.
All right. So Okay, so I don't know if you have questions, also don't hesitate to interrupt me. Yeah, the feedback is not necessarily great, but just yell and I'll stop and try to answer your questions. All right, so you've seen, so as Nicolas was saying, so Q-learning with the table is not very great because, well, first you need to be able to store every possible state action pair right together, which is annoying because it's not going to work for high-dimensional spaces because you won't be able to store all of that. And if you have continuous state action space, that's it, you're done, right? You cannot do that. You cannot enumerate those things anymore. So you need to discretize, but as I was saying, if you discretize for a robot, you're going to have so many states that you cannot store that in a table. All right, so what do we do? Well, what we can do is that you can do Q-learning, and the idea is to replace the table with something we know how to do with machine learning, with a function approximator, right? So instead of having a table, we're going to remove the table and put a neural network instead, right? We're going to still assume that we have a discrete number of actions that we can enumerate, but we're going to assume that we don't care about the state, that the state can be continuous now. So what we do is that we replace the function Q, that is a function of the state and the action, by a neural network that is a function of the state of the action, and some weights that define what's the current approximation, right? So now our Q function is parameterized by theta, which are the weights of the neural network. So the input is still S and A. So I give you a sketch of what it looks like here, and the output is a number that is actually the Q value. Okay. So how do we train this neural network? So as I was saying before, we can write this problem actually. So before, what we were doing is that the left side of the Bellman update equation, right, should be equal to the right side. And if it's not, we try to compute the difference, the error, and try to make the left side become more equal to the right side as we go through that. So we can write this as a least square problem. Basically, what we want is the left side minus the right should be minimized or equal to 0 ideally, right? So we can try to minimize over the parameters of the neural network theta this function where Q, S of A, T, S and A and theta is basically my parameterized neural network. C is going to be a number because this is what I get from my trial on the robot. And then what I'm going the mean over A of T of Q, I'm going to use the Q that I estimate that I fix given my current knowledge about what is theta, right? So I fix my weights of theta, and I just compute the mean for every transitions that I've taken, such that I can have a set of numbers as well, right? So the C and the mean Q, these are going to things I compute and I use as input, desired value for my system, and the left side, the Q of S, A, and theta is the thing that I'm going to vary over theta and try to minimize, and I can do gradient descent on that, typical neural network thing to basically try to get an estimate of Q. Okay, so that's basically Q-learning with functional approximation. So what you do is that you generate some data, so you try some things, you generate some data, you compute C, you compute gamma mean Q, you compute the gradient of Q, and then you minimize, you do gradient descent, you minimize this, and you could keep doing that until hopefully you converge. All right. So that's it. We're done. Now we can basically use a neural network and do Q-learning with a functional approximator, and it's just basically a minimization problem. Gradient descent, pretty forward. Okay. And the set that we need is basically I need to have observed samples, so S, A, C, and the transition ST plus 1 to be able to compute the mean.
We have a question from the room.
Yeah.
I will do this, Andrea.
Yeah.
Okay, here. I was wondering two things. First, is there any advantage using a neural network other than a Bézier polynomial, for instance? Because they're both universal function approximators, so why use a neural network? And second question, is there any way to minimize without fixing the parameter theta inside the inner minimization of the inside the cost function?
That's a good question. So these are two good questions. First, you can use whatever function approximator you want, and there's actually a huge literature on that. So basically, this idea of using function approximation is nothing new. It's really, I mean, I guess at least since the early 90s, people have been doing that. So it's nothing really new. People have first studied how do you do that with, for example, you try to do a linear approximation of Q. You can do piecewise linear. Then people, well, in the 90s, were using neural network. You can potentially try to do the same with the GP. You can do whatever you want, right? So yeah, you can use whatever function approximator that you want. Here the goal is that I want to go all the way down to the deep RL, so I'm going to use a neural network because I wanted to present basically the DeepMind algorithms. But yeah, you can do whatever you want. For the mean, actually, I don't know. So what I know is that people usually you fix it because then it really gives you data points, and you only need to minimize over theta on the left side. So what you will do after that when you work with continuous state action space, we're going to ignore the mean and we're going to do an actor critic thing where basically we try to get an estimate of what it might be, and this tends to work better. So yeah, so we're going to try to get rid of the mean actually in the latest in a few slides from now.
I think there is for the first question. I think there is another reason is try to think about the quantity of code you need to do to make the same with the Bézier polynomial, and take the derivative out of that, etc. And with neural network, it's super easy. You have here you have 3 matrix multiplication, and that's it, and an activation.
Yeah.
And then taking the derivative of that is just the same complexity. And then it's copying. So that's just if you want to implement your own neural network. And in addition to that, you don't want to do that. You want to download something that is doing the approximation for you. So the neural network are really much easier to set up. And there is also a critical mass that are making the neural network framework for approximation really mature and really easy to implement. So on our side, since we don't care so much for the which is the approximation that we are using, going with neural network I think is a very good idea because of technological reason, not theoretical reason.
I guess there are very good libraries computing polynomials with derivatives as well, no?
Here you want a polynomial in space dimension 100, and defining one Bézier polynomial would not be enough. So you have to partition your space. So Bézier polynomials, we know how to use that in a temporal domain. So that's very easy to set up in the temporal domain because despite the size of the output space, the input space is 1, no dimension 1. Here you have an input space that is of dimension whatever. You want to partitionate that.
No, the input space of a Bézier polynomial is the number of control points, so that is not 1, that can grow. It's typically much larger than 1. Like what Steve is doing, it's using a much larger dimension than 1 forward.
Yeah, but for mapping for approximating a function whose input is dimension 1. And then you do piecewise polynomial, so you won't do only one Bézier, you put several of them, and you partition the temporal line for that. Now partition the temporal the space domain for that. You don't want to do that. I'm not saying it's not possible. It is. You meet a new point and you look if you need a new partition of the space, and maybe it would be very efficient. But in terms of implementing that, it would be really bad. I think just considering what you want to put as an approximator for the policy function, and neural network seems a very good idea technologically. Ludo, there is another question by Carlos.
Well,
yeah.
So I was wondering about regularization. So I'm gonna take there's a paper of Marc Toissan. He's talking about optimal control, and he's playing, for example, between splines and Gaussians, and he say that the splines are not a good idea because your problem is not a move, and you're solving the same number of iterations. So I was wondering if neural network, they can regularize your optimal control problem if we build a memory with this approximator function. That's my question. What is your thought about neural network?
Sorry, can you repeat the last sentence? It cut. I didn't really understand. Or maybe Nicolas, can you repeat it?
I want to know if neural networks can be used to regularize the optimal controller, the DDP controller, for example.
So, I mean, that's something that we're looking into a memo, right? Is to you want to basically build a gas for the policy. And potentially using a neural network to either approximate the Q or the value function and the policy is a good idea, right? Because it actually, as Nicolas said, it's extremely easy to train those things. It's a very mature tool set, and then you can use that as a way to regularize your DDP potentially as a warm start. It just depends how you acquire your Q and your V and your policy. Was it your question? Or?
Well, I was not talking about the warm start. I was talking about adding some regularization cost to make easier the optimal controller.
Okay.
Yes.
So basically, what people. So do you know the guided policy search idea?
Yes.
So that's kind of similar to that in the sense that in guided policy search, what you do is that you build local linear models, then you do DDP on that. And in the DDP, basically what you do is that you, at the same time, you try to train a neural network that learns the policy, not the Q function in this case, in the policy, and you try to make sure that these two things, basically, they don't deviate from each other. So you use the neural network output as a regularizer for the DDP, and then vice versa, when you optimize the neural network, you basically use the input, the output of the DDP to train the neural net. So by doing that, actually, the papers that guided policy search by Sergey Levin claims that it actually makes the DDP more stable and the neural network learning better behaved. We've done some experiments in my lab using that. It turns out that actually for our task we were trying to get a robot to jump, so a simple one-leg robot. The regularization doing this didn't work really well actually, and it turns out it was easier. It worked actually better to separate both and to not use the neural network input as a regularizer to the DDP. So I don't think you can claim that generally this is the case. I think it might depend on the problem.
Well, according to Marco's style, you can always go see him.
We should keep going for the class.
Okay, sorry.
Yeah.
But maybe you can discuss with Ludo during the break.
Yeah, but these are very important questions. But that's good. Yeah. Okay, so now we can just plug in. So going back, so you can use whatever function approximator you want. We use neural network. They have many good properties, and then we're done, right? And that pretty much we have a new algorithm. Okay, so now there's a catch. So yeah, just as I was saying, so we are going to fix in the mean, we're going to fix the theta as the previous theta, so we don't optimize those, we optimize these ones, right? So the problem is that if you just do that, and you just use current data that you get from an episode, the training tends to be unstable. It means that basically it tends to diverge. So either it starts to oscillate and do crazy things, or it diverges and it starts to give you crazy values. And there's a few reasons for that. Is that usually the sequence of observations you get from an episode, so you start to do a few actions and your robot starts to move. You have a lot of correlation between the actions you take and the rewards you get, etc. Just because things are happening in time. And correlated data is usually a huge problem to train in machine learning, right? Because machine learning, usually you try to assume IID, which is not the case when you try to use sequence of observation. Another issue is that a small change in Q can lead to a large deviation in the policy. And that, so basically each time, if you do an update all the time, you might start to create crazy changes, and you start to create a very problematic updates. So it turns out that if you just try to do that, it's not going to work very well. So these people have been looking at kind of heuristics to fix this fitting of the neural network. It's true for any type of a nonlinear function approximator. So this is a behavior that people have seen for this past 25 years, so it's not really something new. There's many different ways of trying to address this problem. Something that turns out to scale rather interestingly is that what people did at DeepMind to do the Atari games playing. So that's basically what I'm going to describe now. That's not the only technique. There's many techniques, and again, I recommend you go to the books I mentioned before if you want to learn about the other techniques to do that. So as I said, the problem is that you cannot just get episodic data and do the training because things are going to go crazy. So the ideas, and I think what is interesting is that they are very, very straightforward. The ideas that people use at DeepMind is that they want to use a replay memory. So instead of basically using the current data you generate to update your neural network or whatever functional approximator you have, you store every data that you collect as you try things in the environment in a replay buffer or in a memory. And then when you train, what you do is that you don't train on the data you just generated, you just randomly sample this memory. And by doing that, you hope that you can remove all the correlations due to the fact that you just were generating an episode. So then there's different ways of building this memory. So for example, another thing that you will see is that states and actions that generate high reward tend to be rather sparse, and most of the basically decisions that you may take and most of the states that you may explore, they're pretty much not very useful to achieve your task. So you can try to bias the way you sample your memory and you build your memory to try to keep only mostly in memory things that generated a high reward or low cost, right? And try to not care so much about things that generated a very high cost. And so you can bias your memory and bias the way you sample your memory such that your queue network will tend to quickly fit to very good data instead of trying to fit to things we don't care about in terms of state and action pairs. This is especially relevant when you start to have extremely high dimensional problems, right? So there's actually a lot of papers that explain tricks to actually sample these things in a smart way or generate data in the memory such that the queue network converges in a slightly faster way. The other trick that they use is that instead of updating the queue network and then using it to generate the next sample all the time, which creates correlations and creates drastic change in policies, the idea is that you use queue network. You use a queue network that is the thing that you train all the time, but you actually use what they call the target queue network, which, if you will, it's a copy of the queue network that gets updated only every so many steps, such that you don't have changes. When you do an episode, you don't change the queue network all the time. You just use your target, you generate data with that, then you update your target queue network with the queue network, such that this tend to remove the instability in the training as well. So that's kind of two very let's say simple heuristics, but it turns out that it works really well. So how does the algorithm work? Well, it's actually very simple. So here you initialize a memory of size n. So the memory is going to contain pairs that has a state, action, next state, reward, or cost. Then you initialize your neural network with random weights, right, theta. Then you initialize a target queue network with weights theta minus, right? So that's what we were going to use in the theta minus I was showing in the minimization before. You said that originally it's just the same as the queue network. And then for each episode, what you do as you did before, you start with initial state, you loop for a certain number of times, you generate your episode. So the way you do it, you choose A, an action. Here we still have discrete actions, we can have continuous states. you use the policy using Q, so you take the max over Q, and you do epsilon greedy. So in 1 minus epsilon, probability 1 minus epsilon, you take the best action, and with probability epsilon, you take an arbitrary action in order to explore a little bit other type of actions. So you take the action, you observe the cost, you observe the next state, then you store all of these things in the memory D. So as I said, there's different ways to, when the memory is full, there's different ways of getting rid of removing a sample from the memory and adding this one. For example, based on the cost, you can actually rank all these samples based on the cost that you got. There's also different ways of sampling from this memory, and if you look at references, the people who cite this paper, there's actually a lot of work that people have explored different strategies. Then you sample a mini batch, so it means a very small number. So usually the memory is very big, right? And you sample a very small batch, so typically, I don't know, 64 or 128 transitions from the memory. So by randomly sampling, you hope that then you get almost an ID setting. Then you do gradient descent on theta using this loss function, which is the least square cost, right? That's what we've seen before. Now again, the left side of the Q theta, that's what you optimize. The right side, which is the mean over A, we use actually the target network, which is Q hat, which is basically use the weight theta minus, right? Which are and we only update the weights theta, right? So the weights theta minus, they do not change. They are a different network, and the weights theta, that's the thing that is the current Q function that we update as we go. And every C steps that you choose arbitrarily, you just reset theta minus to theta. So basically, the actual Q that is used on the mean and use is actually changing slower than the actual update on Q. Okay, and you do that, and hopefully everything works out, and that's a video. So can you see the video?
Yeah.
All right. So that's what happens. Then you can train. So a little trick here. Maybe I should quickly. So sorry. Before I explain everything. So what they did for the training the Atari games, that the input is going to be the pixel values of the image. In order to not train directly on pixel, they basically use convolutional neural network as a first pass to basically extract features, and then they do the DQN over these features. So it allows to already extract interesting aspects of the image. That's just a way to train the system. To pre-process if you want the input. But otherwise, it's exactly the algorithm I just described. And that's what happens, and then eventually it just works, and that's very cool. Okay, so we can play Atari games now. So it actually does work, and you can get a rather decent score in doing that. So maybe a few things not to see is that, so here we have a discrete set of actions, so we still need to discretize the actions. The other thing, there's a few issues, right? So first, this thing doesn't necessarily converge really fast. So you might need to generate a lot of samples and trials, and especially if the cost is sparse, in the sense that you most pairs of state actions, they would generate a very high cost, right? If you think about walking, most of the state action, most of the actions you can take given a given state are going to make you fall. So generating good actions and biasing basically the search when you do the epsilon greedy, maybe you don't want to do necessarily epsilon greedy when you take a random action, but you might want to bias it towards things that might be more reasonable when you try to do a very high dimensional problems. So there's still a lot of issues. People are looking into that, but the basic idea is rather straightforward. And so I don't know if you have any questions. If you have any questions, I'm happy to try to answer them now. Otherwise, we'll make a break where Nicolas will take over and they basically show you how you can just replace the Q table with a neural network first. So that was my first naive example. And it's going to show you it doesn't work very well. And then an implementation of the DQN with the replay memory and the target, etc. And show you how that actually it's also rather straightforward to implement. So you can get it to work with the same models as before, but now you can use continuous states, right? Because we don't really need to discretize and enumerate over the states anymore. All right. Any questions?
I have a question. Why do you need to use deep learning instead of just a shallow neural network? In the case where in Atari you need to take the picture of the game, but maybe in robotics sometimes it's not really image based. Do you need neural network or a deep learning to do that?
No, you're right. Actually, the depth of the network, I think it really depends on your problem. So I don't remember what Nicolas is using. It's most likely not that deep, the network that he's using.
2 layers.
What?
2 layers.
2 layers? Okay, so that's not shallow, right? No, you don't necessarily need a deep network. I'm just explaining this because in the context of the papers that were published with the DQN approach, they were using a deep network, as you said, because they were using vision data. If you use other types of data, and it doesn't really matter. The trick here is really to use the memory and the target function seems to make the network training, whatever the depth of it, rather stable. But yeah, this can work with anything. It really depends on your application.
Okay, thank you.
The shape of the neural network that we are using in RL currently are very uninteresting compared to the very elaborated structure that they have, for example, in computer vision, in particular. So even if you put some convolution in a layer in the very beginning to pre-process your image, after that you have some dense layers that have no structure at all. And clearly there is a lot to do there to understand what are the kind of basic function, basic approximator that are interesting for us in robotics.
Yeah, I think in DQN they have 3 conf layers, but then there's only one hidden, fully connected layer, and then the output layer. So I think it's true that in almost any application, the complexity of that final mapping, a single hidden layer is almost always sufficient. I mean, the recent ETH paper uses, I think, 2 hidden layers.
So is it true that to say that if you don't work with images, you don't really need deep network with convolutional layer, but only a shallow neural network will be sufficient?
No, so you cannot be strict like that. So first, in theory, a 1-layer neural network is a universal approximator. So in theory, you are not supposed to do a deep network at all. And it's just that we know that in practice, you get much less parameters when you put a deep instead of a flat. So you, with the same number of parameters, you get a much better approximator with deep than with flat. And the understanding of that, theoretically speaking, is not very strong yet. And then in robotics, the structure of the deep that we are using is not interesting. And it's not necessary to put the deep. But it's not that deep is not interesting, it's that basically we don't know how to use the deep in robotics for a control problem. Okay. So here the example to use is a deep table. So the deep table is a very very naive conversion of the Q-table algorithm using a neural network. Okay. So it's called deep table, but it should be called network table. That could be a better name. So he's doing the same. He's running episode. This time it's running episode with the pendulum.
Nicolas.
That's me.
And this might be a question for Ludo as well. Earlier, a sketch that Ludo used of the Q network shows it as taking state and action as the input and outputting a value. But I think what I've seen before, and what I wonder whether it's like this in your code, Nicolas, is that the Q network takes exactly the same shape almost as the policy network, so it still maps state to a kind of action space. It's just that given a state, you now get a Q value for every action at that action space, as opposed to kind of querying it with your pairs.
Okay, so maybe I will explain a little bit what is inside this one, and then we will go to the Q learning. So this one you can run it just to see, have a feeling of what is its behavior. So here we are giving the materials for several reasons. First, so that it is a little bit interactive, you're not just listening. At some point you have to put your brain in active mode. We believe it's better for learning. Also we can be a little bit more accurate to answer such questions, not with a schema but with actual code. And also you can use that as a reference. So that's basic algorithm we are giving here, but still the DDPG is pretty close to the state of the art, for example. Same for the Q-learning. So a Q network will be defined that way. Can you read it? It's big enough? Well, you have it on your laptop for putting a little later. So we define the network here to be the input. So it's called a placeholder. That's the place where you will put your values before evaluating the network. Then there is a matrix W, that's the weight of your network. So it is a table. Well, it's a matrix. It has as many rows. Yeah, it has as many rows as the number of states, and as many columns as the number of control. Okay, so you take any column of that, and it would be what you say. So all the Q values for all the Q, all the U you can imagine. So one column is the value that the Q value that you get for any control that you can apply. Okay, and then you have to take the maximum of that. So what we are doing is x, which is an integer, right? It's going between 0 and x minus 1. So any state, any continuous state is mapped to one integer. We will represent that by what we call a one-hot vector. So 0, 0, 0, 1 somewhere, 0, 0, 0, 0. And the 1 it corresponds to the index. So it's a very stupid encoding of an integer, right? And then taking the column of the W matrix, will just be multiplying x with W. So that's what we are doing. The Q value is the multiplication of x and W. The output of the Q value network is all the Q value for all the U's. And then the policy will be the argmax to this output. Okay? That's answering your question for this network, right? So in fact, it's exactly the same encoding of than the Q table. So it's a very stupid way of using a neural network. The side effect is that now you cannot, or you should not apply the Q algorithm, so the simple algorithm we saw in the first time. This time you should take the gradient and apply gradient descent. So that's what we do there. So at each iteration, so we run a number of episodes, so a number of the full trials of the system. For each episode we run a number of steps. That's, each time at each control cycle of the system, you send a new control. You take the triplet x, u, x next that you get, and the reward, and then you make a step of optimization, a gradient descent on your Q network. So a side effect is when you run the system, you can see that it's much slower than the Q table algorithm. See? Because we have to compute the gradient, and then we have to multiply matrices for computing the gradient. So all that takes more time. Not a lot, but still it is more time. So it's longer. On the other hand, well, first, as Ludo said, we put here a very simple content inside the network, but now you can put the content you want. So we put one layer, and you can put multiple layers. And now if you want to put an input that is not discrete, well, you had a full vector, so we put one hot in the full vector, but you put whatever you want, even an image if you want, everything's fine. And the same algorithm is in theory running. Okay. And this algorithm is also much faster to converge than the previous one. So it's slower for each iteration, but each iteration is bringing much more information than the Q table. Okay. So I think that, yeah, 500 iteration and you're gone. In that case, if it's too slow for your computer, I store some values for the network. I did that for all the examples. So that's this line of the code. It's called algotrain. Oh. So in algotrain, in general, it's put none by default. You put pre or full to have a pre-training or full training. In output, you get the rate of success. So you count the number of times you manage to succeed, to solve your problem, divided by the total number. So you have, well, basically here you have a ramp of 1, so it's a little bit below the bisectrice, but it's because you have all these problems that you did not manage to solve in the beginning. Okay. So simple algorithm, very simple, I think, very simple implementation in the code. So it's good that you go a little bit reading this code before going to the DQN code that is more complex. Okay. When running, and that's the same for all the examples, when running, if you hit Ctrl-Z, you get a render. So if during the training you hit Ctrl-Z, it will stop the training for a while and roll out a display for you. Okay? So you see how the system is running. It's a basic inverted pendulum. It will swing and go up. And here, you cannot really manage to get something very accurate. It is not doing the optimal commutation sequence. It's doing more swings than necessary. So the 3 or 4 swings, they're not bringing in energy, and then suddenly it goes up. For the parameters that I put in this pendulum, 1 swing is enough, whatever the state you start with. So just starting from here, like 1 swing, and then you go up and inside. So it's not able to discover that. And I tried to let it run for a long time, and it was not able. This Q table algorithm is not able to solve the unicycle problem. So it's too weak, even for the unicycle, which is still a very simple problem. This algorithm is not able to solve it. And you can see also, right, the very basic Q table algorithm was able to solve the unicycle. We improved with a neural net, and we lost a toy problem. So going with a neural network was non-optimal, right? The first step is costing you. Any question for this one? No. Any remark from Ludo? Computing Q of X and U, we are computing in a row all the Q, X dot. Okay, that's the vector you get at the end. And then in addition to that, there is 2 output layers that are value and policy that will compute the optimal value and the argmax, the max, which is a real Q value, and the argmax, which is a policy. Okay, that's these 2 layers that are here. Well, a bunch of tricks to compute that, not very interesting. And the optimization function that we will use, and this target network that Ludo described. So we will not work with only 1 Q network. We will work with 2 Q networks. One that we will use to get the policy, and one that we will optimize. And we will make the one that we use to get the policy track the one that we are optimizing. So that it's a kind of low-pass filter on the parameters. You don't want to directly apply the parameters that you are optimizing because they are changing too quickly. So you are low filtering them. Low-pass filtering. Okay, any question about the structure of the network? See again, it's not a deep network, it's only 2 layers because I have a configuration space in the input. I don't need any convolutional space, convolutional function to extract some features. So the second part which is interesting, I think, is the algorithm itself. So in the algorithm, there is first, so again, we run for a number of episodes. For each episode, we run for a number of control cycles. For each control cycle, well, first we play something on the robot. We collect the sample that we get from the simulation. And instead of directly working with this sample, we put that in a batch so that we can break the temporal correlations. So we don't work with the last 10 iterations, for example. We work with 10 samples that we take randomly from the batch. The batch is a queue, so when there is enough information in the queue, you forget the past. So the long, the early trial that you did that are very likely very bad, you tend to forget to remove them. Which means that also you have to sample constantly in all the dimensions of the space, because otherwise you will forget. Then we take this batch size. I think it's 68 in these examples, 64 in this example. So we get all the XU, X2 pairs and the reward, and then we optimize the AGB residual. So that's done on the Q value network, and then we move the Q value target network a little bit in the direction of the Q value network. Okay, we'll continue. So in the beginning, he's doing. So here the algorithm only works with the unicycle because I don't have the unicycle is in this example it is continuous in input and discrete in output. So you can take any continuous state. I'm not using the one odd vector, but the controls are 1,000 possible controls to be sent to the system. I did not dare doing this mixed version of the pendulum. I think the most interesting is the actor critic for robotics, so I focus on this one. So hence you only have the unicycle. So you can see that in the beginning, the unicycle is acting randomly, right? It's doing very crazy stuff. I'm changing the dataset so that I can boost a little bit the training. So I run the optimization, I think, for 1,000 episodes and save the parameters of the network. So after 1,000 episodes, you get something like that. It's not bad, no? It's not the best you can imagine, but the system is already pretty good. I put a terminal cost, so if he exactly managed to go to the origin and stabilize at the origin, you get an extra reward of 20, but it was not sufficient. Still, there is still some oscillation, so I would need to tune a little bit more this part to adjust it a little bit better. And what? Keep improving. Not that much. It's already a pretty steady state here. Okay. So in that case, for the parameters tuning that I did, without either the replay, the batch replay, or the target network, I'm not able to solve neither the pendulum or the unicycle problem. Okay. And then the exploration strategy that I put, it's a noisy, greedy optimization strategy that I corrected, Ludo, thanks to the bug you found. I was not at all noisy in the beginning. But I was not able to solve complex problems, like just the unicycle, but driven in force. So I'm changing the force to the wheel, and not the velocity of the wheel. Already is not able to solve it anymore. So we need to boost a little bit the policy, the search strategy, and I would need also to play with the parameters. So get some computation time on a GPU farm, run several versions of the algorithm, tweak a little bit the parameters on each of them, and get a better solution. So get the best parameters for that. So that basically, this is Python coded, but it's the state of the art in terms of implementation. There is some tricks that are missing, but not much. What is missing is the tweaking of the algorithm. Okay. Questions? I think if no question, we can maybe have a 10-minute break and come back for the last hour of class. Right? So not more than 10 because Ludo has a time constraint, he has to leave a little bit before 5. So if we take more than 10 minutes, well, we will have to not explain sufficiently well the actor critics, the DDP.